Hi everyone and welcome to this new video about steady-state analysis. We will consider a RLC circuit in this example and we will use the node voltage analysis. What is given? We have the following circuit with R1, R2, L and the capacitor C. These are the values. And we have the voltage source Vs, which is given in the time domain as shown here. The following we would like to calculate the steady-state voltage across the inductor VL and the steady-state current through the resistor R2, which is I2, and all of them must be expressed in the time domain. What we do is we will transform our circuit parameters given here first in the frequency domain. We will carry out the calculations and afterwards we will transform back to the time domain such that we have the VL and the I2. That's actually the procedure. So we have to first determine the frequency representation of the components. Now R1 and R2 are pure resistive, so these stay same in the frequency domain. We have to determine the reactance for the L and the reactance for the C, for the capacitor and inductor. And we have to transform this expression for the voltage source Vs in a phasor domain. So phasor expression, in a polar expression. So I will start first with the expressions for the reactances. So the XL, which is the reactance of the inductor, is XL is omega times L, and omega here is 8,000, which is shown here in the expression for the Vs. So I can have 8,000 times 9 millihenries, which will give me 9 times 10 to the minus 3, which is 72 ohms. If I now carry out the calculation also for the capacitor, which is X of C equal to 1 over omega times C, can you substitute the values for omega 8,000, and for the capacitor you have 5 microfarads, so you have 5 times 10 to the minus 6, and if you do the math here you will get 25 ohms. Okay, and the final one, which is the Vs, I can now make Vs is equal to, because it is in the cosine representation and we have also a 40 degrees phase shift here, I can just use the amplitude and make the phase of 40 degrees. If this was a sine, I have to add also minus 90 degrees to come up to the cosine. So that's actually very important that you have the cosine as your reference. So we have the Vs, which is a vector here actually. So you have the amplitude of 6 and the phase will be 40 degrees. And the units are just still in volts. So that's actually for the first part, to convert the reactances and convert the expression for the voltage source in the phasor notation. What we now like to do is the following. I will set up the equation to carry out the nodal analysis. So I will define a point in the circuit. So I will define this point. I will make just that X. And I will use Kirchhoff's current law at point X. That is actually what we do in nodal analysis. If you do that in DC domain or AC domain, it doesn't matter. In DC domain, you don't have frequency dependency. In the AC domain, because it is for steady state, it's just one frequency. So it is exactly, in essential, exactly the same procedure. But you have to be very careful with the calculation of the reactances and also taking the Phasor notations for your sources. So let's start. What do we have? We have actually the following. The current of I1, of R1, I mean, I1, this one in the Phasor notation, will split in the current of the inductor and also the current through this branch, through R2 and C. So I can write the following. I can say I1 will be IL plus I2. And IL is this current. Again, all of them in vector notation. So if you now unpack this expression, I1, which is this voltage Vs, which is already given here, minus this voltage at point X, but it's actually VL, and divided by the R1. So I have the following. Vs minus VL divided by R1, which is I1, is equal to this current, which is actually the voltage at this point, this is VL, divided by its impedance. So overreactance in this case, and that is J times the XL. So I have the VL divided by J times X of L. plus I2, which is again the same voltage because it is across the same branch, it's parallel, but I have this time a series combination of R2 and the capacitor, so I will have R2 minus JXC. So I have actually everything here, R1, R2, XL and XC, and also VS, but I only have a known VL, which is actually also the required value. So if I now solve this expression and determine the polar representation of VL, I can transform to the time domain. I will have the first required value, which is VL in time domain. So if I now move on, just substitute everything I have, which is 6. I will do that here on the left side. So I have 6 phase 4 degrees minus VL divided by 10 is equal to VL divided by J72 plus VL divided by 20 minus J25. Okay, that's actually for this expression. So what do we do next? Now we can convert all of them, all these expressions, in the polar representation. That will be handy when we divide the terms here, so I will do that also. So the next step will be 6 phase 40 degrees minus VL divided by 10 ohms actually, and that is in Phasor notation 10 ohms at 0 degrees. I have a VL divided by, it will be 72 with 90 degrees because of the J, it is pure imaginary. And I have here the third one will be VL divided by the vector length of this one, will be square root of the 20 squared plus 25 squared. That's actually a very familiar formula. So you will have 32, and the phase of that will be minus 51. We have dealt with these examples in the complex numbers and phasors video, so you can also consult that video if you want to more know about this. I will leave the details in this video out. Okay, if I now carry out the calculation, what do? I can now simplify this, and I can determine the VL. So I have the following. It will be 0.6 phase 40 degrees minus 0.1 VL with a phase of 0 degrees still. And this will be 1 over 72 VL phase minus 90 degrees. Because if you divide by the phase will be 0 degrees here, minus 90 degrees will give you minus 90 degrees. And plus 1 over 32 VL phase will be plus 51 in this case, because it is 0 minus minus, and it will give you plus 51 degrees. Now we have all the required values actually in a phasor notation and also in a polar expression. So what I would like to do is, if I want to add or subtract several terms, it is better to have the expression in the rectangular expression. So I will transform all of these in the rectangular expression, which will be handy when I carry out analysis. So what I do is the following. I will have the 0.6 and the cosine of the 40 degrees plus J sine of the 40 degrees. This is for the first term. For second term I don't have to do much, but I will again show it. It's 0.1 VL times the cosine of 0 plus J sine of 0 degrees. And the other one, for the on the right side, the first term will be 1 over 72 times VL, and it will be the cosine of minus 90 degrees plus J sine of minus 90 degrees. And for the last one, 1 over 32 times VL, and you will take the cosine of 51 degrees plus J sine of 51 degrees. And that's actually for the final one. If you now calculate this all these terms of the sines and the cosines, and you multiply by the 0.6 and all those terms outside the brackets, you will have for yourself a reduced form of this expression. So you will have the following. I will just give you the result, and I will again group all the VLs together. What I have is the following. I have 0.45 plus J 0.386 minus 0.1 times VL, which is equal to 1 minus J 1 over 72 times VL plus 0.0197 times VL, and the last one will be J 0.0243 times VL. I will now group all of the VLs, because I have the VL here at the left side. I have also a couple of terms for the VL on the right side. I will leave these terms at the left side, so I will all the terms of the VLs will be placed to the right side. So what I have is the following: VL, and I will now place the real parts first. So what I have is the following: it will be 0.1197 for that, for the real part, and for the imaginary part I will have plus J 0.014104, and for the left side it will stay at 0.45 plus J 0.386. Now the next step will be converting the expressions of the left side and right side in the polar representation, because I can then divide them very easily such that I can determine the VL. So what I do is I will determine the polar representation of this one and the polar representation of that one. So that will give us 0.593, a phase of 41 degrees, and the other one will be VL times 0.12, phase 5 degrees. Now if I now want VL, VL is 0.593 degrees, 593 with a 41 degrees, divided by 0.12 phase 5 degrees. So if I now do the math again, you divide the magnitudes and you subtract the phases, you will have 4.94 phase of 36. And this is of course in volts. And we have actually the expression of the inductor voltage now in polar representation. If I now transform this in time domain, so in time domain, what do I have? I have the following: the VL as a function of time, which is actually question A, will be 4.94, just the amplitude, cosine, and still the same frequency, so it will be 8000 T, and the phase will be 36 in volts. So what you actually recognize is this one will place actually as an amplitude for the cosine term, and this phase will be placed here in the brackets and in the parentheses as 36 degrees. And you will use again the same frequency omega, which is 8000 radians per second. Okay, now that's for the question A. Now for question B, I would like to determine the current. So let's move up a little bit. So what we have is the current through the R2. Now, since I know the voltage across this inductor, which is just VL, it is the same actually the voltage across these two elements. So what I can do here is I can use the voltage at this point for the current what I want to calculate for this branch. Now the current through this branch is this voltage VL divided by the total impedance. And if I know the current for that impedance, it is exactly the same as the current through R2. So I will use for question B the total impedance and the voltage across the total impedance, which is actually the voltage we have determined. And I will use the Phasor, the polar expression actually for that. So I will move a little bit to the right and move to the question B. So this was question A. So the whole business here, let me make it clear, this was A. And now we will move to question B, which is determining the current. So I have I of 2, which is the total voltage at that point X, which is VL, divided by the total impedance seen at that point, so which is R2 minus Jx of C. And if I now substitute the values, what I have is for VL was 4.94, phase of 36 degrees, and R2 was given as 20 minus xj, we have minus jxc, we have calculated as 25. So if you now convert this part also in the polar expression, you can do the division more easily. So you have the following: 4.94, that will be just the same, divided by the 32 for this part. So you transform from the rectangular form to the polar representation to 32 and a phase of minus 51 degrees. If you do the math again, just divide the magnitudes and you subtract phases, you will have 0.154 and a phase of 87 degrees in amperes. Now, this will be of course also converted to time domain. So what will be that we have the time domain expression for the I of 2, which is the required value. So that will be 0.154. Again, the cosine, same frequency, 8000 T, and we have a phase of 87 degrees and in amperes. So this is for the last one. Remember, this is the amplitude and this is the phase, and you will need to use again the cosine. You will need to use the 8000, just a template. So the only difference here is just actually this amplitude and this phase. It depends actually what you have here. This cosine and the 8000 T will be exact same for all of the answers we have. Now, okay, that's actually for this example, for the RLC example. We will continue with other examples, with other analysis methods like a mesh current analysis, superposition, Thevenin, Norton. So keep in touch and don't forget to share and like, and I see you next time.